So if you're working on designing an AC RLC parallel electrical circuit for a generator, please stick around for this lecture and we'll go over some design fundamentals. So here we have an engine driving an AC generator with an electric AC clutch, and then in this case we're building a generator from scratch, so we have all the hardware components, but we still have to build an RLC circuit to interface the output from the generator to measurable and useful AC electrical power. In this case we're going to work with an 8,000 watt AC true power generator, and so we've set the hardware up to the earth ground with an on-off switch, and we have a base RLC circuit. So now we have to figure out what will be the values of the resistor, inductor, and capacitor, so we can use this step-by-step calculation method. And this is based on designing an AC RLC parallel circuit with a power factor of 1.0 so that the inductive reactance and capacitive reactance are equalized by implementing an AC resonant frequency design method, 1 over 2 pi times the square root of the inductance times the capacitance. So if we were to just isolate the L times C, or LC, to X, we could then solve for X and then find its square root to separate them into equal values. And so one will say, what about the power factor? In the case of the circuit itself, it can be designed at a power factor of 1.0 even though it's interfacing with an AC generator with a power factor of 0.8. So what will happen in the circuit is that it will function as a purely resistive circuit with the maximum base reactive power, and so it becomes a very reliable circuit with respect to unpredictable loads. So it's not always going to be set up that way in the industry. So if you're custom designing and building an AC RLC circuit for a generator, it's often recommended to design it as an AC resonant frequency circuit, and then the circuit will take what it needs from the generator's 0.8 power factor, which then becomes a phase angle of 36.87, either leading or lagging the voltage or the current depending on the load. So it actually works out very well, and it takes the least amount of time to build. Getting around the equations is then just the fundamental design template as specified here, and so then we just finish off with the AC apparent power, voltage times current without the power factor, and it is a volt amp apparent power equal to the true power. And again, these are just 2-pole generators, 8,000 watts, 72.2 RMS amps. And so then at the actual performance output, it becomes a resistive, purely resistive circuit where the current neither leads or lags the voltage in phase. So the one obstacle to circuit designers is the best answers come from the best questions. So a good question to ask is, can you design an AC RLC electrical circuit with a power factor of 1.0 to be matched to a generator with 0.8? And yeah, and the answer is yes, you can. It's actually encouraged, but it's often not talked about. So thank you for watching this lecture and have a great day.